Good morning, everybody. Welcome for the first seminar colloquium from the IAA, Instituto de Astrofísica de Andalucía, here in Granada. And today we will have the talk by Dr. Rubin Sanchez-Jansen from UK Astronomy Technology Center. And he will talk about the high multiplex and multi-IFU spectrograph for the ELT. So Rubin will be properly introduced by Dr. Isabel Marquez. So Isabel.
Thank you, Rene. Good morning, everybody. First of all, thank you very much for being here for this, as Rene was saying, first Severo colloquium of this year, 2024. I take profit for wishing you a great new year, 2024, to you all here or online. So thanks for being here. And of course, thank you very much to Dr. Rubin Sanchez-Jansen for having accepted our invitation to come here to provide us with this, I'm sure, successful talk about MOSAIC. Rubin Sanchez-Jansen is an astronomer at the UK Astronomy Technology Center in Edinburgh, and he's honorary fellow of the University of Edinburgh since 2021. Rubin graduated and received his PhD in 2009 from the University of La Laguna with a thesis project at the IAC, the Instituto de Astrofísica de Canarias. After postdoctoral stays at Chile as ISO Fellow and Hertzberg Institute of Astrophysics in Canada with a Plaskett Fellowship, he is currently astronomer, as I said, and project scientist at the UK Astronomy Technology Center, which belongs or is, I don't know how it is, but from Science and Technology Facilities Council, right? Where he contributes to the development of scientific instrumentation and facilities for ground and space-based astronomy, from the ultraviolet to the near-infrared, with a particular emphasis on future missions. He is principal investigator of the UK instrumentation program for the ELT, as well as project scientist of MOSAIC, the multi-object spectrograph for the ELT. He has been PI for the UK contribution to CASTOR, a proposed UV space observatory, also board and science team member for VT Cubes, the next high-resolution near-ultraviolet spectrograph, UK board member for the Mauna Kea Spectroscopic Explorer and the Wide Field Spectroscopic Telescope, and coordinator for the H2020 Opticon Technology and Innovation Network. His research program revolves, I love that word, around the evolution of galaxies, with a particular focus on low-mass galaxies and star cluster systems in the nearby universe. And he's talking today about MOSAIC, this high multiplex and multi-IFU spectrograph for the extremely large telescope from ESO. So thank you very much again, and the board is yours.
Thanks so much, Isabel, for such a nice introduction. And well, I wanted to start thanking the Severo program for the invitation, and of course, in particular, Carolina, Jorge, and Pepe for being the sponsors, let's say, for this visit. So today I wanted to introduce MOSAIC, which, as the title says, is the second generation instrument for the Extremely Large Telescope, or ESO's Extremely Large Telescope. Basically, I'm an instrument scientist and co-project scientist for the project. So let's see, is this working now? It's not. Doesn't matter. I'll move this. Then. Yeah, I see here now. Let me see now. Now it moves. Right. So the ELT, in case you haven't seen it recently. It's becoming pretty real, as you all know. It's a 39-meter aperture telescope, segmented, fully adaptive optics controlled. And this is the status as of, I think, last month or so, on Cerro Armazones, about 40 kilometers from Paraná Observatory in northern Chile. You can see how it's already progressing incredibly. You can see the dome. So the ELT will see its first light. Right now, it's planned for late 2028. That's the current schedule for the telescope, and that basically makes it's going to be the first of all the ELTs, way ahead of the US TMT and GMT telescopes. So it's, with a 39-meter aperture, it's going to completely transform astronomy, especially in 2030, right, when we actually are going to be exploiting this facility routinely. And again, it's not only the aperture advantage, right, that gives you the d squared sensitivity advantage, but you got the d to the 4 advantage once you plug in the adaptive optics correction. So again, the ELT is a telescope that it's fully adaptive. So the M4 is a fully adaptive mirror, and so actually the telescope per se does not deliver a scene, right? The image quality of the ELT is complete rubbish until you turn on the AO and the deformable M4 mirror starts operating. So we all know that telescopes are the way we collect the light, but they're nothing without their instrumentation suite. And the ELT has a very ambitious instrumentation suite that matches the ambition of a telescope per se. So why we are building MOSAIC? So the instrument has a number of very high-level, top-level requirements. The first one, perhaps the most obvious one, is to exploit the large field of view and collecting power of the ELT, right? So the ELT delivers a field of view, technical field of view of about 10 arc-minutes. But from the first generation instrument, this is the largest field of view that we'll have access to. So Mikado will provide a 1x1 square arc-minute imager, long-range spectroscopy, but you can see how the rest of the AO-corrected ELT field of view is entirely unused, right? And this is basically what is the niche for a multi-object spectrograph. Then the other 3 main points that drive the design of the instrument is that it has to provide spectral coverage in both the visible and the near infrared. Something that I'm not going to be putting a lot of emphasis on is the ELT coating. So the ELT is optimized for the infrared because that's where the AO correction is really, really significant. And so the coating for the ELT is optimized for the infrared, but extends all the way to the blue. But the first light instruments have a very clear focus on the infrared. So for the next generation, there was a clear drive from ESO to have instruments that extend as blue as possible. The other one is that it shall provide a number of resolving powers. And then also a mixture of modes, providing both high multiplex or relatively high spatial resolution to be able to resolve objects spatially, not just to collect the light. So this is the ELT instrumentation suite in, let's say, parameter space, right? This is a plot from Susie Ramsey's Messenger article. So here you've got spatial resolution in milliarc seconds versus field of view of the instrument, and here we got Mikado, which is an imager and spectrograph, and you can see, as I said, this is the largest field of view of Mikado 1x1 square arc-minutes. This is Harmony, the integral field spectrograph. Metis, the mid-infrared imager and spectrograph. And it says high-res, it should be Andes now, which is the high-resolution spectrograph for the ELT. And you can see how this is where MOSAIC lives, right? So it's the coarser scales of the ELT, because we are correcting for the full field of view, not a small area, but the widest, by far, etendue of the telescope, right? So it's going to be a field of view around 7.5 arc-minutes in diameter and unobscured. And then in parameter space of wavelength coverage versus resolving power, what I said before, we've got Mikado, which does spectroscopy at intermediate resolution in the near infrared mostly. Metis, that focuses on this mid-infrared regime, very niche for the ELT as well. Again, should be Andes, not high-res. The visible and the IR single object, but a resolving power of 100,000. And then the parameter space for MOSAIC lives here. So a range of intermediate to low, let's say, of 5,000 to 20,000 resolving power, indivisible from 0.39 to 1.8 microns. And this is where you see the complementarity of all the different ELT instruments. Now, to put a bit MOSAIC in context of other MOST instruments, right? Because we're now living in this era where to do follow-up large imaging surveys, HLD becomes like kind of the driver parameter, right? And so on multiplex. So you can see here, telescope diameter, the x-axis versus telescope multiplex, how many objects you can observe in one pointing. Of course, the ideal is this diagonal. You want the largest possible aperture and the highest possible multiplex. But you can see where most instruments that exist either in operation or in construction, they live in this part of the parameter space. We are in this 4 meter to 8 meter class telescopes with multiplex of a few thousands at most. These are planned instruments for the mid-2030s, mid-2040s, and you can see where the emphasis here is to have, again, 8 meter, 10 meter class telescopes, but with very large multiplexes. And then we've got the instruments for the ELTs. So it's clear that we cannot compete in terms of area in the sky footprint with the smaller telescopes that can have very fast optical designs. The actual advantage for the ELTs, naturally, is the aperture, right? It's the sensitivity. And there are two very useful scaling relations, right? If you're observing in spectroscopy a background-dominated source, your limiting flux is inversely proportional to your telescope aperture, right? So if we compare, for example, the VLT with the ELTs, you get an advantage of almost 2 magnitudes deeper for a fixed exposure time, right? That gives you an increase in terms of the volume of objects that you can observe, the factor 10, right? Typically. But perhaps more interesting for spectroscopy is that if you go for a source-dominated observation, right, you want to for an object that is relatively bright, and what you want to do is, for example, relatively high spectral resolution, right? Because what you want is not just detect a faint feature, but you want to detect a feature at high signal to noise to do actually precision abundances, for example. Then the limiting flux goes as the square of the telescope area, right? So for relatively bright objects, MOSAIC and the ELT in particular are going to provide a magnitude advantage of almost more than 3 magnitudes, right, at fixed exposure time compared to the VLT, right? That gives you, for example, for galactic studies, an increase of 100 times more in terms of the volume that you can access with an ELT. So who is the consortium? Who is MOSAIC? Who is building this instrument? Complex graph. I don't want you to pay attention, but just to show you, it's a really, really big project that is led by France. France is the PI country, but it has 14 institutes from 8 different countries. It's a huge consortium, basically because it's a very ambitious project that it's going to require a lot of resources. So the PI is Rosette Pillot, who a lot of people will know very well. She's based at in Marseille, in France. And I want to highlight that she not only is the first female PI of an ELT instrument, she's the first ever female PI of a VLT instrument. Of an ESO project, which I think is something quite remarkable and for something we're quite proud of. So this is Rosé is leading the project. And what I wanted to highlight, of course, is that it's a really, really big team. So the science team is currently over 260 members of the ESO community. And Mathieu Puech from Paris and myself are the project scientists. So we coordinate the development of the science case for MOSAIC. And then the technical team is led by Eric Prieto, who's the project manager, and Miriam Rodriguez, who's the system engineer. And it's lots of different work packages almost 90 people working to actually construct this and build this instrument. And of course, I want to highlight the participation of Spain, and in particular the institute here, the IAA, right, where there's a big contribution, and together in the electronics of the instrument. And so I'll talk about the schedule later on. So as I said, MOSAIC is a multi-purpose instrument for the ELT, as most multi-wavelength spectrographs are. This is not a surprise, right? And so in terms of the science, we are dividing the science in 6 different science working groups. I'm going to go very, very briefly over, what are the science goals for these science working groups. But again, it's a workhorse instrument, right? Most multi-wavelength spectrographs are. So the first science working group is on first light galaxies and reionisation. And of course, I want to highlight here the role of Carolina, who is actually coordinating together with Matt Hayes and Nicolas Laporte, this science working group. And the goal here is to actually basically constrain which are the main sources that reionize the universe, and to provide a physical characterization of these sources. And how we're going to do that is through measurements of metallic lines in the UV, in the rest frame UV at high redshifts, higher than 7, not just emissions, but also in absorption, thanks to the high sensitivity provided by MOSAIC, to constrain the escape fraction, the Lyman continuum escape fraction, and to characterize the properties of the ISM, and to actually also, I think this is perhaps something relatively new, thanks to Webb, right? We've been finding AGN at very high redshifts. And so the idea of MOSAIC will be also to actually follow up and provide a detailed characterization of those AGN and their role towards reionization. Science working group 2, we call it inventory of matter, but it's what you would call basically tomography of the intergalactic medium and the circumgalactic medium. And the main survey right now is mapping of the cold gas distribution at redshifts of 3.5 more or less on megaparsec scales by doing quasar line of sights and reconstructing the Lyman alpha forest. And so you can provide reconstruct through tomography basically the 3-dimensional distribution of the neutral gas at these redshifts. And the niche here for MOSAIC is this. You cannot cover again area, but you can go very deep. So it's an entirely different redshift range than most instruments can do at redshift of 2, more or less. Third science working group is on galaxy evolution and mass assembly. So the idea here is basically just to actually constrain the growth of galaxies at let's say higher look-back times. Here I'll go again three main science cases: the environmental large-scale structure of high redshift galaxies, the properties of the ISM and the evolution of the stellar populations, and then the last one is emphasis on the study of sub-L star, relatively low mass galaxies at redshifts 2 to 4. And here, this science working group has a big component using the IFUs. The idea here is to do a survey of hundreds of galaxies at redshifts 2 to 4 with spatially resolved information. So data cubes using the multi-IFUs. For a relatively large sample of objects to go beyond just the number statistics and the integrated properties. So science working group 4 is galactic archaeology. And the main emphasis here, again, we have a relatively small area, so we cannot really do galactic archaeology per se. We're not going to cover the entire galactic halo because we don't have enough area. So here it's more selecting low mass galaxies and star clusters. This low mass regime, the divide between the star clusters and low mass galaxies, the ultra faint dwarfs, and to be able to do precision spectroscopy down to the main sequences. So this is an example of an ultra faint dwarf galaxy here. For example, this is Draco 2. So this galaxy has a total luminosity of 300 solar luminosities, right? It's really faint. And basically, there are about 7 stars in the red giant branch of this object, right? So you cannot say much You cannot say anything about the intrinsic metallicity, the metallicity spread of this object. So you have to go down to the main sequence to be able to do this. And you can see the magnitudes here. If you want spectroscopy of tens or hundreds of stars for this object, you need to go to 23rd, 24th magnitude, right? And you need an ELT to do that. And also, same thing with the inner galaxy, the obscured galaxy, going to study star clusters in the inner galaxy. And of course, then the sensitivity of the ELT is what gives you the depth and going well, peeling into the dust regime and peeling into the bulge. Stellar populations beyond the local group, so let's say local volume. Again, there are a few key science cases. Spectroscopy of individual O-type stars out to 5 more or less 5 megaparsecs. The Sculptor group, for example, and this is more or less the signal to noise that you can obtain spectra for an O-type star, and you can see that all the way to 5 megaparsecs, you're over 30 and signal to noise ratio. So you can actually characterize the physical properties of these massive stars out to 5 megaparsecs. Same red supergiants out to more or less tens of megaparsecs, distances like very good cluster, and especially Fornax in the south. And then also young superstar clusters to distances more like, 100 megaparsecs. And finally, there's one science working group that is a relatively new one, and actually we have not developed the case, and it's not a driver for the design of the instrument, which is transients and multi-messenger astronomy, right? This is a very key science case going forward. And so we have a science working group that is small right now, but they're starting to look in what way could MOSAIC contribute to actually following up spectroscopically faint transients, right, in the era of Rubin and SST, for example, right? And the idea here, or even LISA in the late 2030s, and the idea here is that MOSAIC would provide spectroscopic characterizations of the environments of the host galaxies and the environments of transients, energetic transients. So these are the 6 science working groups that we are working and with which we are developing the case. And so, but I haven't actually mentioned what is MOSAIC in detail, right? What is the instrument? How are we going to actually build the instrument? And I guess this is just the simple way of showing it. So the design of MOSAIC is a very modular instrument. It was built like that in purpose. And the idea here is that we deliver 3 different observing modes that can be used in parallel. So basically, we get light from the ELT. We have an adaptive optic system. Then we have a complex focal plane that delivers 3 different types of observations, as I mentioned. So we do a multi-wavelength spectroscopy in the visible, and we feed with fibers a visible spectrograph. We can, in parallel, do multi-wavelength spectroscopy in the infrared, because with fibers we feed an infrared spectrograph. So at the platform, at the native platform of the ELT, there will be 2 separate spectrographs, an infrared and a visible. And then we have these multi-IFUs that only operate in the infrared because they want to resolve spatially objects, and the AO correction is only good enough in the infrared to do so. And they share spectrograph with the MOS, right? So the idea is that we provide this different capabilities to the community that is flexible and that lots of different science cases can benefit from. So I'm going to go over just a bit of details of these different subsystems. I'm not going to talk about the spectrographs. The infrared spectrograph is an evolution of the MOONS, VLT MOONS spectrograph. The VIS spectrograph is an evolution of the one for MOST on parallel. But I wanted to highlight, for example, that the idea of the AO is basically that we're going to provide a seeing improver. Again, we are not providing very, let's say, diffraction limit correction, because you can only do that over very small fields of view. Just to give you an idea, the field of view of harmony, which is a first light integral field spectrograph, when at its diffraction limit regime is less than 2 arc seconds, right? So you can only correct to the diffraction limit very, very small spatial fields. MOSAIC, on the other hand, is going to be correcting a field of view of 7.5 arc minutes, right? So the quality of the correction has to be, by necessity, quite small. So the correction is going to be ground layer adaptive optics. It's basically ground layer tomography. And what you do is that you use 4 lasers and 3 natural guide stars to correct for full tip tilt correction and higher order corrections across the entire field of view. So basically, just to give you an idea, what MOSAIC will do is that in the visible, below, let's say, 6,000 angstroms, you will get an image quality that is similar to what you will get in terms of just the seeing. It's not the seeing, but it's kind of in terms of the scale, it's going to be similar. In the infrared, all the way to the H band, which is our reddest band, then the full width at maximum would be more like 0.3 arc seconds, something like that, right? So again, it's just a seeing improver, but you are correcting the full field of view or of the ELT to be able to do so. The focal plane is very, very complex. I'm going to go into the details, but basically this is the 10-minute field of view, technical field of view of the ELT. So we provide science over 7.5 minutes in diameter. These are the cutouts for the laser guide stars that I mentioned before. So this area we cannot use. This for laser guide stars. And you can see here there's these little tiles. So in these tiles is where the positioners live. And we have 300 of those in the focal plane. So we can have up to 300 positioners here operating simultaneously. The positioners is a very novel concept. And again, I don't want to go into the details, but this is how they look like. They're quite chunky. But we have, prototypes already. The main idea here is that you get the light from here at the top. You have an optical relay system. You have an atmospheric dispersion compensator to be able to get the light into one spot and not have differential losses. And at the bottom of all this complex mechanism is where the fiber bundle is going to live to actually collect the light and bring it through fibers onto the spectrograph. So I said fiber bundle because when I say fibers, we don't have fibers, we have bundles. So for every visible and infrared MOS at low resolution, we have a bundle of 7 hexagonal objects together. The reason why this fragmentation is needed is because the ELT has a very large plate scale. It's 3.3 millimeters per arc second, right? And so you cannot actually build a fiber that is big enough to actually collect all the light from a PSF. And so you have to fragment it. And so every object is going to be mapped by 7 different objects. And also this makes the design of the spectrograph much smaller because the size of your slit and your optics is divided by it's determined by the size of one of these fibers and not the entire bundle. But basically, I'll go over the numbers. These numbers are not very accurate because of recent revision of the design. I'll show the numbers in detail. But the idea here is that you have several hundred of the visible and the infrared MOS bundles. The high resolution in the visible, you actually have to slice even further because the only way of reaching the resolving powers that we need is to reduce your entrance slit further, right? And so this is why you can see that these bundles are smaller than these ones. It's just to increase the resolution, spectral resolving power. And then the IFU has I'll show it there. It's going to be 8 of them. The aperture is not 2.5, it's 2.2 arc seconds in diameter. With a spectral size of 150 milliarc seconds, and you can deploy those across the entire 7.5 arc minute field of view. So this is actually the modes that we have in MOSAIC and the multiplex. So as I said, we have the 2 MOS modes. So we have one visible spectrograph, and here we go from 390 nanometers all the way to 950 in one shot. I'll have something about the spectral settings with bigger fonts. And then in parallel, you can do the infrared from 950 to 1.8. When I say in parallel, is that you do it on the same focal plane, but it's not on the same object. It's different positioners that are feeding the visible and the infrared spectrograph. They live together on the focal plane, but you're using the 2 spectrographs simultaneously. And this is also in one shot from 950 to 180. In terms of multiplex, how many objects you can observe, in the visible at low resolution, it's 140 with a subfield diameter, this diameter here, of 0.7 arcseconds. At a high resolution, it's also 0.7, but we have a lower multiplex because we have more fibers per object. And in the infrared, both low and high resolution, is 200 objects with 0.6 arcseconds in diameter. Then the IFUs, as I said, there's going to be 8 of them. And this is the number is really limited by the number of detectors that we can afford. Basically, it's how many pixels we have available. It's 8 of them. The field of view is going to be 2.2 arcseconds in diameter. That's the longest direction of this hexagon. Sampled at 150 milliarcseconds. I mentioned that the PSF is going to be more or less a full width of 0.3 arcseconds. So we are kind of like critically sampling that PSF with this spatial scale. And so again, spectral settings perhaps what people are more interested. As I said, so in one shot, we get 390 to 950 in the visible at resolutions, I said, larger than 4,000. So the medium resolution is more like 5,000. And then we have, for this is a 2-arm spectrograph. So we also have, on one of the cameras, we're going to have 2 high-resolution ratings. And the other camera is going to have also two high-resolution ratings to cover these spectral ranges at a resolution of more or less 18,000. That's mostly for galactic studies. But you see that we can cover from the very blue all the way to more or less the calcium triplet at a resolution of 18,000. And as I said, the full visible in one shot at resolution of more or less 5,000. In terms of the infrared, right? So this is the infrared. So I didn't show you, but these dashed lines here are the requirements of the instrument, and the lines are what we achieve. So we are above the requirements all the time. So this is the infrared, 950 to 1.8 in one shot at low resolution, again of about 5,000, and then just one high resolution band at about 1.6 in the H band, which is kind of the apogee band, again, mostly for galactic studies at a resolution of about 18,000. So I'm getting close to finishing. Just when the timeline for the development. So right now the instrument is in its phase of preliminary design. We started earlier this year, and we expect to complete. So this is a technically paced schedule, and we expect to complete it around 2025. We have a very critical point, which is called the funding review in 2026, when the consortium has to demonstrate that we actually have the funding to ESO, that we can build the instrument. And this is critical in 2026, because that's when we actually are going to decide what we can build, basically, right? For us to be able to build what I've been showing you, you have to go to ESO and say, I've got the funding to do that. If we don't, that's where the difficult discussion about these scopes is going to take place. Then the final design review is in 2028, at the beginning of 2028. And then we have a 4-year final construction, very aggressive schedule, to be able to have what we call the preliminary acceptance Europe, which is we assemble the instrument, we test it in France, and ESO gives us the green light to ship it to Chile. That's in 2032. And then in early 2034, the instrument goes to the ELT, it gets plugged and installed on the Naismith platform, and we commission it. And ideally, if all goes well, by mid-2034, we start doing commissioning and science verification, and we start with the guaranteed time observation surveys. I didn't mention it. Of course, the way ESO pays the consortium for all the contribution in terms of both hardware and effort is in terms of GTO, guaranteed time observations. And we are looking at getting around 130 nights, even though that's still to be negotiated, spread over 8 years. And that's just for the consortium, right? So that's 130 nights that belong to the consortium to carry out a number of surveys that we are actually working to define right now within the science working groups and the science team, together with, of course, the MOSAIC board. So yeah, you can see there it's 10 years ahead of us at least worth of work, but this is what these very complex instruments take basically. And so this is just my last slide, and again, just the take-home message here is that MOSAIC will really excel at very deep pencil beam surveys, right? We're going back to fields of view comparable to what we used to have on the even 4-meter telescopes, and even force-like on the ELT, right? 10 minutes at most, but of course very, very deep, high sensitivity. And so of course the niche for MOSAIC is faint sources, right? Going after those faint sources or relatively brighter sources at a relatively high spectral resolving power, but providing very high survey speeds. So the idea here is to open new parameter space and actually provide spectroscopic follow-up to all these new facilities that are going to be doing imaging and radio surveys of the sky, right? And MOSAIC will be like the go-to instrument to follow up these very faintest sources that are going to be discovered in the next decade or so. That's me. I can take questions now. Thank you.
Thank you very much, Rubin, for this wonderful talk. So now the talk is open for questions. Please, in the room, maybe Jorge or Carolina, if you want to manage the questions, go on, please.
Thank you, Rubin, for this nice talk. We have time for questions. Yes.
So multiplex just means how many individual objects you're going to be able to observe in one shot, right? So when I say multiplex of 200, it means that you can observe 200 objects, but the light is you have to think as if it was just one fiber. So it's spatially unresolved. You don't have spatial information for those 200 objects, right? You get an integrated spectrum for those objects, even though I showed you that the bundle is going to have 7 different, you don't have spatial information for those 7 bundles. You have spatial information for 8 objects. That's the multi-IFU. That's similar to VLT cables, right? So you deploy 8 mini IFUs over the field of view, and for those 8 objects, you do have spatial resolved information at a spatial size of 0.15 arcseconds. Those are the 2 modes in the infrared, correct? So we have more or less 200 objects without spatial information in the infrared, or 8 objects with spatial information. And then in the visible, it's 140 objects if you're doing low resolution, or 85 objects if you're doing high resolution. So that's part of the complexity of MOSAIC, which is the parameter space of different configurations is very large. And agreeing with the community and with ISO in which direction we should push, it's taken us years, right? Because you can optimize in very different ways, right? But yeah, that's where we are right now with the design, and I think that's where we're going to go ahead with. Yeah.
Thank you.
Yeah, thanks. Eventually.
So for clarify,
yeah.
That it is not possible to get the simultaneously the infrared and the optical, the visible spectra for the same object.
Yes.
I mean that you have to split it in some way and later to
yes. Yes, correct. There are 2 reasons, one scientific and one practical, I would say, for that, and that is a bit historical. The scientific one was that, of course, everyone knows that if you get the spectrum, if it's in one shot, it's easier because you have the full spectrum, and then you have more discovery space, right? But we did not have a single case, a single science driver that required the full coverage from 0.39 to 1.8, right? when we were actually driving the requirements and translating them into technical specifications, there was no particular case that required that full coverage. But the practical one was that MOSAIC up until early this year, last year, 2023, did not have an atmospheric dispersion compensator, right? The reason was that when we had looked into it, basically it's huge relay optics to be able to have basically an ADC, right? What I mean with huge is that the relay system to do this thing was 3 mirrors of 2 meters each at the platform. So it was just crazy, right? We just couldn't build it. And if you don't have an ADC, you can have differential losses, right? Because you cannot track the parallactic angle. So if you observe an object with a relatively small fiber bundle of small aperture, atmospheric dispersion is big enough that you either lose the light on the visible or you lose it in the infrared, right? You cannot optimize. And so, of course, that drove us into having this design where we had different spectrographs and you could observe simultaneously, but not, in parallel, but not simultaneously. Now, I did show you very quickly, the new thing, what's been new is that now the ADC, this is a very novel concept. Now the atmospheric dispersion compensator lives locally behind the positioner. So we can have 300 positioners on the focal plane. And behind each of these, there's going to be these sets of prisms right behind them. So there's going to be 600 of those providing local correction of atmospheric dispersion behind the focal plane, right? At the back of here is where the ADC is going to live. So now we can provide this atmospheric dispersion. Now, the issue here is that if you were to do the full multiplex, right, the 300 objects simultaneously in the vis and in the near, then we will also need much bigger spectrographs because we will need more pixels on the detectors to accommodate the 300, right? So that's why in the end, we got to a compromise where we said, okay, we can observe in the visible and in the infrared simultaneous, in parallel, in the sense that, no spectrograph is sitting there idle. So we're collecting all photons, but it's different objects. So if for one object, you want the full spectrum, then you have to, finish your integration and then swap, right? And you say, okay, I observe 150 objects with visible, 200 with infrared now, and then I swap and I do the 200 that I did with infrared, I do now with the visible, but it's in 2 shots, not in 1. So that's a disadvantage, but it was a compromise that we had to reach to be able to provide both the multiplex and the spectral coverage. So the ADC, this atmospheric dispersion compensator, is the one thing that is allowing us to do the visible in 1 shot. Without the ADC, atmospheric dispersion losses were so bad that in the previous incarnation of the design, the visible was done in 3 bands. So not even the visible was simultaneous. We had to observe first the blue, then the green, then the red to just get 1 visible spectrum because the losses were significant. And so this is a huge improvement because now you get what do you mean by several? Yes. No, I wish, but the problem is that for air masses of more than 1.3, atmospheric dispersion, blue to red atmospheric dispersion is big enough that the PSF spot is bigger than the bundle, right? So you would get the blue PSF would be here, and the red PSF would be here, and the green one would be in the middle. So the problem is, again, that the bundle is quite small. It's 0.7 arc seconds. The reason, again, being that the plate scale of the ELT is so large that if we wanted to have a bundle of 1 arcsecond, which is what we actually wanted to get all the light, then you would have to add another ring, and that decreases the multiplex, because in the end it's traces on the detector that you have to remove. So it's this trade-off between, it's a difficult trade-off, right? How much of the PSF spot you cover, how much objects you got, how much spectral coverage you got. So yeah.
Questions?
Well, thank you very much. Impressive instrument. I have a question about the design of the objects were advanced. I mean, are they fixed in their orientation, or they have different? I'm sure they are aware about the difficulties of the linear with when they do the different. So can you explain a bit?
Yes. So that's basically that's a real difficulty. So the IFU have several difficulties, especially precisely for what you said, dithering and going stacking, right? Repeat observations, particular if you're going to faint objects. Let's say you want to integrate 20 hours on one source because it's a very high redshift galaxy and you want the IFU. Controlling the positioning of the IFU is very difficult because the plate scale of the ELT varies quite a lot on small timescales, right? And so making sure that you are pointing where you think you're pointing to be able to actually blindly stack your data cube, it's one of the most difficult things that we are facing. And actually, to be honest, we are not there yet in terms of demonstrating that we can achieve that. Right? There's a lot of simulations because the problem with the ELT, and for a MOS instrument in particular, is that, as I said, it's a fully AO telescope. And this is the first time ever, right, that we build instruments that depend so much on the AO system. Everything, the guiding, the acquisition, the pointing, everything depends on what the AO can achieve. Right, that's why we're so heavy on the AO, right? You see the design of the focal plane, right? And it's crazy that you have 4 lasers, 3 guide stars, and that's to precisely control the plate scale very well to be able to know, the absolute world coordinate system to make sure that, again, you go back the following night or 3 nights later and you're positioning. But to answer your question, we have no control about the rotation, unfortunately. We think we're going to be able to control where we point, but the actual location, rotation of the hexagon. And so this, and then reconstruction, PSF reconstruction, given this difficulty of the PSF varying. So again, the PSF of this AO system on timescales of typical iteration times of 300 seconds, it varies. It's not a very nice, well-behaved PSF, right? So we're still working, and actually, people like you guys that are experts on IFU data, we're gonna actually need input from you to actually decide, how is gonna be the way that we're actually gonna be reconstructing these data cubes and knowing what PSF we're actually getting on the actual data. So there's challenges there. The IFU adds a level of complexity, right? Because again, it's not just one MOS instrument; it's a MOS and a multi-IFU together, and it's pushing the design and the requirements in different directions. So a lot of work for us to do, and I think that demonstrating before final design that we have achieved this precision, that we can go blindly to a location and again, as you said, integrate for 20 hours. It's gonna be difficult. So let's talk.
Thank you.
We'll need it, yes.
Hi, Rubin. Thanks for this very much informative talk. I have a different kind of question. What is the situation now of the whole project regarding the agreement with this or the next phases of construction?
Yes. Yeah, so that's a very important question, and as people that have been involved and here, people have been involved for a while, they know that it's taken us quite a lot of time to actually get started with phase B in particular, Phase A was finalized in 2018, and Phase A was only started last year. So it took a lot. So right now, we have an agreement with ESO. And so this Phase B has been split for the first time ever in 2 different phases. And we are in this thing called Phase B1, which ends with this milestone, this review. It's called the Specification and Architecture Review that we're having in September this year. And that one is basically ESO want to make sure that, the architecture is sound, and that we've flown down specification into different subsystems adequately. Now, after that, we need to agree with ESO, and ESO have to go to council to get approval to go into Phase B2. That brings us into this final phase, which is the preliminary design review, right? So we are pushing very hard to ESO, we're pushing ESO very hard to guarantee that once we have passed the SAR, this Specification Architecture Review, we go into the next phase quickly. For example, Andes, which is the high-resolution spectrograph, it's also a second-generation instrument like MOSAIC, but they started before. They had already a more mature concept, so they passed their SAR back in September, October, and they have been given the green light by ESO to start this Phase B2 soon in 2024. It's not still specified the exact date. So the problem is that ESO are really lacking resources. So ESO don't have enough people to follow up these projects together with the first light instruments. So as a reminder, technically, there's 4 first light instruments, right, for ESO, because one of them is Morpheo, which is the adaptive optics facility, right, which is considered an instrument, even though it's not doing science per se. It's just an enabler to the other instruments. And so ESO are really lacking resources to follow up these projects properly, right? So on the one hand, there's this tension. ESO would like us to go a bit more slowly. The consortia, once we're in Phase B, we want to go fast, right? Because everyone is going to their funding agencies, requesting the resources that we need to go ahead, right? So I don't know if this answers the question. In the short term, again, we have a technically paced schedule, but I think we're going to be modulated by ESO quite a bit. I think MOSAIC is going to go a bit more, a bit more slowly than Andes, but we have a very clear mandate, and our project manager is pushing very hard to be able to go to Chile around this time and not much later. Mostly, again, as I said, because it's not healthy for a big consortium to spend too much time stuck in different phases, and also because we have commitments by several partners that they have to spend funding resources before certain years, right? But again, it was a milestone to get ESO to agree on to getting started on this Phase B, and then the big one, as I mentioned, is going to be this one, the funding review. Again, for people perhaps for the more junior people in the audience, right? The scheme of developing these instruments for the ELT and for ESO in particular changed dramatically for Andes and MOSAIC, because up until now, always ESO was the one that was paying for the bulk of the hardware. So the hardware contribution was always brought by ESO to the project, and the instruments, the consortia, brought the effort and perhaps additional hardware if it was needed, right? But ESO changed this scenario, this scheme for the second generation instruments, and now the consortia have to raise all the funding, everything, right? The hardware and the effort. And that means that we actually have to demonstrate at this review, at this milestone, that we actually have those fundings secured. We have to have them in the bank, but they have to be identified to be able to go forward. And so, that is a really tricky situation where, the funding review if we are at 85%, let's say, in terms of, for example, the hardware contribution, ESO have said, look, we'll talk, right? Like, ESO might chime in. If we are at 40%, that might be the end of the instrument, right? If you're so far into getting your funding, and the difficult situation, which is where we are right, as of today, is what happens if you're in between. What if you're at 65%, right? Because there you're far, ESO won't be able to chime in 35%, and you're far from delivering. And so that means that's why I said that perhaps that's where, if we find ourselves in the situation, which we hope we won't, we might have to discuss, start discussing about potential descopes of the instrument, and that's a very nasty situation, right? That's at the board level, right? Not even the project office, right? But of course, our PI and our PM are working very hard trying to identify resources and partners that can come up with all the funding needed, so that when we get to the funding review, we're in a good position to go ahead.
More questions? I have one.
Yeah, of course.
Can you say something about the GTO surveys? Or
Yes. Yeah. I to be honest, I put together the science description of the different science working groups, and I thought I'm going to put one slide on the GTOs, and then I forgot. So the GTOs. The organization of the GTOs, as I said, so what we have agreed with ESO right now is that we get 65 nights for the effort contribution, and an amount that is still to be negotiated, but we are pushing to be of the same order. That's why I mentioned 130 nights more or less. But again, that's TBD for the hardware contribution. But again, it depends on how much we provide in the end, how much ESO provides. So we're thinking 130 nights. So the structure of the GTO servers, just to be clear, it was decided by the board that the entire time is going to be pooled, right? So it's not going to be, it's not going to be IAA gets 1 night, LAM gets 20 nights, the ATC gets 10 nights. It's not like that, right? It's pooled by all the partners, and we go there and we design these surveys, right? Now, how we design these surveys is the process that we embark right now. The idea is that we identify the science working groups. We are identifying key science cases that are unique to MOSAIC, right? What we think is going to be the killer science in 2035 that only MOSAIC will be able to do. And we start designing surveys that we think will maximize the scientific return of this, right? So, for example, most likely, for the extragalactic surveys in particular, several surveys will live in parallel in the same pointing, right? Because of what Rosa was asking, right? Of not being able to do visible and infrared at the same time, right? Most likely we'll do something like, for example, a galaxy, high redshift galaxy survey with the infrared, while at the same time with the visible, you're doing the Lyman alpha tomography of, again, same fields, because cosmological fields tend to be well-known and unique, right? But different targets for different science cases that are running in parallel on the surveys. Now, the exact breakdown of how these surveys will be designed, there's going to be a ad hoc panel that is going to be appointed down the line by the board that is going to actually take the information that the science working groups and the project scientists provide, and they're going to say, okay, well, respecting more or less this complicated situation about, leadership of contributions, these are going to be the main surveys that MOSAIC are going to do. And then we're going to have discussion on, who leads what papers, right? So the idea is that we're going, let's say, bottom up. So we first have a pool of very good ideas of what MOSAIC should do, and then they get progressively distilled into surveys that can work together and that provide a good science return. And we write this thing called the MOSAIC. It's going to be the first, the red book, and then there's going to be the red book. This defines the surveys for MOSAIC. And the key thing, I think, the difficulty, to me, the big difficulty is what I mentioned, that the GTO time is going to be spread over 8 years, right? And that's a challenge, right? Because, from the time you start to the time you end, 8 years have passed. So how do you, and this is the work that, mostly Matteo and I have to work really hard on, how do you ensure that on your first year, you're doing enough exciting science that you have an impact, right? But that also the stuff you do at the end is impactful and it's not just added value, right? It's something just really important that you have only, you can only achieve after 130 nights. So it's going to be, and I guess that's going to evolve, right? I don't think the Red Book and the surveys are going to be frozen at the beginning, right? Because you as you go, things will change, right? We're talking 2034 for the first light if all goes well, but then the end of the GTO is going to be 2042, right? So things, I guess, are going to be evolving, and new projects probably will be added to these surveys as the landscape changes, right? And new data come in, and we're going to have Lisa and Athena potentially, and who knows what, right? So there's going to be, there has to be some flexibility built into that process to make sure that the surveys are impactful. But I don't know if that answers more or less. But if people have other questions about the GTOs, yeah, feel free to ask. And so
more questions.
So yeah, the most junior people in the audience, you're going to be the ones enjoying this instrument. So start thinking about it.
So before thanking again Rubin for his talk, I remind you that at 4 in the afternoon, he will be in the Sala Polivalente for an informal meeting for those of you who are interested in talking to him about MOSAIC or your favorite science case. Okay? Thank you again.